Designer Len Nemi had several design goals in mind when he was designing the Sisu 1A sport sailplane. He wanted the highest performance with the least amount of drag, and he did a couple of things to the wing to ensure this. First of all, he selected an NACA laminar flow airfoil for the least amount of drag, and he also designed forward sweep into the wings. Now, many designers will actually twist the wingtips, built-in twist into each wingtip so that the airflow hits the wing at a different angle throughout the wing, and that allows the ailerons to continue to bite the air and give the pilot control during a stall. By adding forward sweep, Nemi eliminated the twist and reduced the drag, and he also induced the air to flow from the wingtips into the wing root. This allowed the ailerons to continue to bite the air and gave the pilot control during the stall. Now, the other benefit to having forward wing sweep was that Nemi could join the wings behind the cockpit without having to build some kind of a complex and heavy bridge structure to actually enclose the cockpit and hold the wings at the same time. The Sisu that is in the National Air and Space Museum is actually a world record setter. In 1964, it became the first motorless aircraft to fly in excess of 1,000 kilometers. It flew from Texas to Nebraska in over 9 hours and was a world record that still stands today as the first sailplane to fly 1,000 kilometers.
Lift and drag are always connected, and perhaps never more so than when a plane enters stall. On a cold winter day in 2009 in upstate New York, Captain Marvin Renslow and First Officer Rebecca Shaw were at the controls of a Bombardier Dash 8 Q400 operated by Colgan Air. The flight was a short 52-minute hop from Newark, New Jersey to Buffalo, New York. Unfortunately, the flight would never arrive at its intended destination. As the aircraft approached the Buffalo airport, the weather conditions there were a wintry mix of light snow, fog, moderate winds, and a temperature of 1 degree Celsius. The captain and first officer noted ice accumulation on the wings and windshield as they approached the vicinity of the airport. After lining up with the final approach course and lowering the landing gear and the flaps, the aircraft's speed began to decay more than normal. As the autopilot worked to hold the aircraft's altitude, suddenly the wing lost a lot of lift and the aircraft began to fall out of control. Only about 20 seconds after the first sign of trouble, the flight crashed nose first into the ground and the aircraft exploded into flames. Sadly, this incident resulted in the death of all 49 passengers and crew, along with one person on the ground. Let's talk about what happened and how a routine flight could go so horribly wrong in just a moment. The fundamental aerodynamic principle at work relates to how lift and drag work together on a wing to govern the properties of flight. Since the amount of lift generated by a wing is directly related to its angle of attack relative to the oncoming flow, higher angles give more lift. If the wing needs to generate a higher lift coefficient, for example to fly more slowly, then the aircraft can be pitched up to a higher angle of attack. This is because the lift must remain equal to the weight, and as the airspeed goes down, the lift coefficient must go up. The primary way that a pilot can increase lift coefficient is by increasing the angle of attack of the wing as the nose is pitched up. This increases the amount of flow turning and increases the downward deflection of the wake downstream of the wing. And from Newton's third law, the lift increases. In the Colgan Air 3407 crash, accumulation of ice on the wings and windshield increased the aerodynamic drag. The presence of the ice disrupted the smooth flow of air over the wings, and the roughness of the ice led to much higher viscous drag. Also, the ice would likely lead to small pockets of separated flow, which would significantly increase the pressure drag. The overall impact of this ice accumulation is more sluggish aerodynamic performance that should be counteracted by increasing the throttle setting on the engines. Since the pilots did not add power to overcome this additional drag, the aircraft began to decelerate. The autopilot, which controls the aircraft's altitude, its pitch, roll, and yaw orientation, continued to pitch the aircraft to higher angle of attack in order to generate enough lift to maintain constant altitude. There is a limit, however, to how much lift can be generated by a wing, or how high the angle of attack can go before significant problems are encountered. Beyond a certain critical angle of attack, the flow streamlines cannot successfully negotiate the aggressive curvature near the leading edge of the wing, and the streamlines depart from the wing's curvature. In other words, the flow separates. This flow separation event occurs because the boundary layer has insufficient momentum to counteract the adverse pressure gradient that the flow is working against. The stronger the curvature of the flow streamlines, the more intense the changes in pressure will be, and the harder it will be for the flow momentum to overcome the increase in pressure required to recover back up to high pressure at the trailing edge. And the most significant consequences of flow separation over a wing is a dramatic loss of lift, which is called stall. The onset of this flow separation can happen very quickly as the wing is pitched to higher angles. It's a very grave situation in an aircraft, since the aircraft will begin to fall when lift is lost during a stall. Each aircraft has specific stall characteristics. There is a physical angle of attack and corresponding minimum speed at which it can fly. Any lower flight speed will result in a stall. This is precisely what happened in the case of the Colgan air crash. The insidious thing about ice accumulation on the wings is that it changes the stall characteristics of the airplane, often in unpredictable ways that the pilot may not recognize. When ice accumulates on the wing, it changes the shape of the wing, adding increased roughness and curvature, making it much more prone to flow separation. Thus, the flight speed at which an aircraft will stall can dramatically increase in icing conditions. Let's look at ice on the leading edge of a wing. There is a resulting flow field around it. Clearly, the airflow is disturbed significantly and the wing is no longer aerodynamically clean. The problem, though, is that the accumulation of ice is extremely difficult to predict. The exact shapes that result from various conditions are a result of the complex interaction between three-dimensional aerodynamics, heat transfer, and the size, temperature, phase, and density of water droplets that interact with the wing. This is actually an active area of research to understand and reliably predict how ice accumulates and inform strategies for mitigating the problem. For the Colgan air crash, the Dash 8 aircraft would normally be flown at an approach speed of 145 knots with no flaps in order to be well away from the stall speed of 118 knots for a clean wing. However, in icing conditions, the limiting stall angle of attack decreases and the stall speed goes up by an unknown amount due to the uncertainty of ice accretion. Thus, safe operating procedures in icing conditions require that the approach speed be set 25 knots higher than normal at 170 knots in order to add a margin of safety. So if a pilot encounters unexpected stall condition, what can be done? Is all hope lost? Thankfully, it is a recoverable situation as long as there is sufficient altitude and the pilot responds quickly and accurately. In order to recover from a stall, the pilot must actually point the nose down in order to decrease the angle of attack and re-establish flow over the wing that follows the curvature of the airfoil. Wait a minute, this seems counterintuitive. The pilots must actually push the nose down while descending in order to recover from a stall. This procedure is the exact opposite of our gut instinct, which would lead us to pull up to somehow arrest the descent. The problem with pulling up in an attempt to arrest a descent is that it actually makes the stall worse. Pulling up to increase lift only works when you have smooth attached airflow over the wings. But pulling up in a stall only exacerbates the stall, leading to even greater loss of lift. Take a look at this plot of the lift coefficient as a function of angle of attack. The stall is indicated by the inflection point in the curve. Before stall, the pilot can easily increase angle of attack in order to increase the lift. However, the limit to this trend is stall, and beyond stall, the exact opposite trend occurs. Further increases in the angle of attack result in lower lift. Sadly, this is exactly the mistake that the captain of the Colgan air flight made. He pulled back on the control yoke, pitching the aircraft up as high as 19 degrees angle of attack, which is well beyond what any commercial airliner can handle. This high angle of attack made his stall condition even worse, leading to asymmetric lift on the wings, causing the aircraft to lose directional control and spin into the ground. The proper procedure for the pilots would be to push the nose down and throttle the engines to maximum speed. This condition would be held momentarily until a lower angle of attack and higher flight speed is established, which allows the wings to recover their benign lift-producing characteristics. Only after lift has been restored can the pilot pull out of the descent and recover to the original flight altitude. Now you may be wondering about what can be done to prevent such a horrific situation as the Colgan air crash. Wintry weather is a routine occurrence in many places throughout the world. Why don't we see more airplane crashes due to icing conditions? Well, there are a number of aircraft design aspects and operational procedures that counteract the icing problem. Aircraft that routinely fly in icing conditions must be certified with systems that can effectively remove ice from the wings. There are several strategies for doing this. Many larger jet aircraft use warm air that is bled off the compressors of the jet engines to circulate through ducting right behind the leading edge of the wing. The hot air heats the leading edge, melting any ice that is accumulated and preventing further ice accumulation in most situations. Another strategy is what is called a weeping wing, where a large number of small holes are manufactured in the leading edge of the wing and an antifreeze fluid is pumped through the holes and used to melt the ice. A third strategy is to use inflatable rubber boots on the leading edge of the wing. These rubber sleeves have air pumped into them and they inflate just like a balloon would. The expansion of the boots causes the ice to mechanically break up and shed off the surface. Each of these concepts must be tested extensively for robustness and certified for aircraft to be able to fly into known icing conditions, what we call FICI certification. These de-icing and anti-ice systems are effective at removing ice in flight when there is air flowing over the wings to carry the ice away. But what must be done when an aircraft is covered in snow and ice before it pushes back from the gate? This leads to the required de-icing that routinely occurs at airports in wintry conditions. If there is any visible ice or snow accumulation on the aircraft, it must be de-iced before taxiing for takeoff. Aircraft taxi over to the de-icing pad, where trucks surround the aircraft and spray a de-icing formulation over the wings, engines, and fuselage. This fluid serves to remove any ice on the aircraft and also has an anti-ice component that helps prevent further ice accumulation while the aircraft is on the ground under wintry precipitation. Let's now return our attention to the aerodynamics of lift and drag and how they interact on a wing. The previous discussion for controlling lift by changing the angle of attack is true for a given airfoil and wing geometry. Essentially, this is a pilot's perspective on how lift can be controlled. But let's take a step back and consider what an aircraft designer might be able to do to control the lift produced by an airfoil or wing. Given that the lift is directly related to the turning of the flow streamlines, we might be able to achieve greater flow turning for an airfoil at a given angle by changing the curvature of the airfoil. The amount of curvature is referred to as the airfoil camber. A highly cambered airfoil with convex curvature, of course, will generate significant lift even at zero angle of attack. In contrast, a completely symmetric airfoil with exactly the same curvature above and below the midline then will produce no lift when it is at zero angle of attack, since there is no net downward deflection of the flow behind the airfoil. However, if a symmetric airfoil is oriented at an angle with respect to the flow, then it will produce lift. Since positive and negative angles of attack present the same situation to the oncoming airflow, a symmetric airfoil can just as easily fly in inverted flight. For this reason, symmetric airfoils are very useful on aerobatic aircraft, which spend a significant amount of time in inverted flight. The airfoil has the same aerodynamic characteristics whether the plane is right side up or upside down. Now, what if we want to somehow increase the lift coefficient beyond what the airfoil is naturally capable of doing? What if we could shift the stall angle of attack to a higher angle? If we could do this, we could fly the aircraft much more slowly. And if we can fly the aircraft more slowly, we can dramatically decrease the runway length required to bring the aircraft to a stop. Just look at this example of a bush pilot in Alaska who is in very slow flight and somehow managing to land the aircraft within an incredibly short distance. This enables the pilot to drop the aircraft into very tight, remote landing areas in order to deliver food, fuel, and other necessities in even the remotest corners of Alaska. For this reason, the aircraft is like the pickup truck for Alaskans. It connects remote villages to civilization in ways that are otherwise impossible. The aerodynamic trick that this pilot employs is to actually change the shape of the airfoil in flight. On this aircraft, the pilot has deployed a flap, which changes the shape of the airfoil to enhance flow turning, resulting in a greater downward deflection of the flow streamlines. Other devices, known as slats, can be extended from the leading edge of the airfoil to achieve the same purpose. And this is not such an esoteric approach. Commercial airliners also use slats and flaps to actively change the shape of the wing on final approach to landing. By changing the shape of the wing, the aircraft is allowing the pilots to fly the airplane with a higher lift coefficient and enabling a lower flight speed while still maintaining lift equal to weight. The designer's challenge, then, is to create a functional flap and slat system that will reliably extend and retract under all circumstances, will retract into an aerodynamically clean configuration for efficient cruise, and at the same time will provide high lift at low speeds. Let's look at the aerodynamics of flaps and slats in a little more detail. There are several different kinds of flaps that can be used. One of the simplest methods is to install a hinge in a segment of the wing, somewhere near the trailing edge, to allow the pilot to drop the last portion of the wing down at an angle. This flap design is most commonly found on small general aviation aircraft due to its relative simplicity and low cost. The aerodynamic function of the flap is to simply increase the camber of the wing, but in a way that can be changed in flight. This allows for a wing configuration that is optimized for cruise, which is when only a moderate lift coefficient is needed due to the high flight speed, while meeting the need for low drag. At the same time, the use of a flap allows for the airplane to fly much more slowly than it normally can with its cruise-optimized wing. In this plot of the lift coefficient, we can see that the lift coefficient for a given angle of attack is increased dramatically when the flap is deployed, and that higher lift coefficient will allow a pilot to fly more slowly. Now let's take a look at the other end of the spectrum of system complexity. A commercial airliner such as the Boeing 747 has a very complex high-lift system that allows it to have an approach speed as low as about 160 miles per hour, but still cruise at a top speed of over 600 miles per hour. The 747 has a series of both flaps and slats which work together to dramatically increase the camber of the wing. The slat is a strongly curved airfoil that deploys from the leading edge. At the trailing edge of the 747's wing, a whole series of flaps deploys, not just one. Each flap is set at a successively higher angle, allowing the flow to do a better job of negotiating the strong curvature without separating. This flap and slat system produces an amazing amount of flow curvature without separating. Now, you may be wondering why aircraft designers don't simply design the wing with these great flaps permanently deployed. The reason is drag. These high lift configurations not only produce a lot of lift, but they also have a lot of drag. Extra drag really isn't a problem when the pilot is trying to slow down on the aircraft on final approach, but extra drag is a problem in cruise flight. By the way, when I mentioned that the 747 has an approach speed as low as about 160 miles per hour, that still seems pretty high, right? That's 2.5 times the speed that we normally drive down the highway. Yet the pilot is able to successfully steer the aircraft to maintain the center line of the runway and bring the aircraft to a stop within about a mile. Up until now, we've mostly been thinking of the wing's aerodynamics in a two-dimensional sense. But a quick look at the wing profile reveals that the wing is anything but 2D. Across the span of the wing, there is a substantial variation in the distance from the leading to trailing edge, which is termed the wing chord. There are several reasons for this taper of the wing, and one of which relates to the three-dimensional stall characteristics of this wing. And here is the key point when it comes to the three-dimensional nature of wing stall. It is really important for the wing to stall at the root rather than at the tip. Why? Because the aircraft has control surfaces called ailerons that are located near the wing tips, and it is critical to maintain attached flow over the ailerons in order to maintain roll control. If the flow were to separate at the wingtips first, the ailerons would lose effectiveness in the slow, unsteady separated flow, making it much more difficult for the pilot to maintain control of the aircraft during a stall event. Unfortunately, some of the natural aerodynamic characteristics of swept-back wings that we see on most commercial airliners will naturally lead to stall at the wing tip first. But aircraft designers have a few tricks up their sleeves to make sure that stall happens inboard first. One strategy is to twist the wing across the span, such that the inboard portion is permanently set at a higher angle of attack than the wingtip, which will lead to root stall first. Now, in an airplane, it's really important to have the wing stall at the root rather than at the wingtip. The way aircraft designers do that is with the stall strip. It's a triangular piece of metal right here in the leading edge of the aircraft that creates a disturbance which forces stall to happen here first at the wing root. Once stall occurs at the inboard portion of the wing, it's also very important to constrain the stall to that portion of the wing and not let it propagate outboard. Designers can do this by installing a wing fence, such as what we see on the MiG-15. This aircraft has highly swept wings, making it susceptible to poor stall characteristics. So this very large fence will keep the flow separation constrained to only the inboard portion of the wing. It's a remarkable addition to the MiG-15, since it's such a large device relative to the wing and adds significant weight and drag. The severity of 3D stall must have been a vexing problem that forced the designers to include such a large fence, but it is a good example of how critical it is to address the wing stall problem. Let's take a closer look at what actually happens during a stall event. Now, stall may sound like something very dangerous to be avoided at all costs, but it's actually a routine maneuver that is flown often during pilot training. Moreover, smart pilots will often intentionally practice stalling an aircraft just to make sure that the correct recovery procedure is ingrained into our muscle memory. The key factor that will make our stalls safe is altitude. A stall performed at a good altitude of several thousand feet above the ground gives us plenty of time to recover. A typical stall recovery can be easily done within just a couple hundred feet. Most stalls only become dangerous if they happen unexpectedly when the aircraft is close to the ground. Our plane in this demonstration is a Cirrus SR-20, a small general aviation aircraft. A common way to illustrate the aerodynamic effects of the stall event is to tape pieces of string all over the top of the wing. We call these tufts. When the flow is attached, we expect that the tufts will lie flat on the wing and be aligned with the airflow. However, when the aircraft slows down and encounters stall, the tufts stand up and move about quickly due to the unsteady, chaotic flow of air during a stall. Once in flight, I initiate a stall by slowing the aircraft down gradually while maintaining level flight. In order to begin the stall, I pull the power back to idle. At the same time, I also gradually increase the pitch attitude, or angle of attack, in an effort to maintain level flight. As the speed goes down and the nose goes up, we'll eventually reach a critical angle of attack where the stall occurs. As I decelerate and pitch the nose up, a loud, obnoxious noise sounds in the cockpit. This is the stall warning horn, which is required on aircraft. Its sole purpose is to warn the pilot of an impending stall so that corrective action can be taken before a full stall develops. In this case, I'm ignoring the stall warning horn. Now, as I enter the stall, the tufts show how the airflow is changing. The initial evidence of unsteadiness in tufts appears for a time before the stall rapidly overtakes the full chord of the wing. Also, the stall occurs first on the inboard portion of the wing and stays limited to that region of the wing due to the presence of the stall strip on the leading edge of the wing. And how we recover from a stall relies on that counterintuitive procedure. Even though our gut instinct tells us that we should pull back on the control stick, I must push the nose down a bit and add full power until I recover to normal flying conditions. Tufts on the outward portion of the wing show that the flow is still attached there. Now, each aircraft has its own stall characteristics, some more benign than others. Loss of control of the aircraft is the leading cause of general aviation accidents, so it's really important for pilots to be well prepared for this event should it occur. We're now going to shift gears and talk about a distinct form of drag that is actually related to lift. We call it induced drag, because in a sense, this type of drag is induced as a byproduct of generating lift. It only appears when we have a lifting surface, such as a wing. Let's start with our high-level view of lift. All lift must be a result of a net imbalance in air pressure acting on the wing. There is always lower pressure on top and higher pressure on the bottom of the wing. If we view the aircraft from behind, we can see that this pressure difference must extend out to the wingtips. Also, it's important to recognize that flow naturally tends to flow from regions of high pressure to regions of low pressure. This is the source of winds in our atmosphere, which are always blowing from high to low pressure. In the case of the wingtip, the air will naturally tend to flow around the wingtip from the bottom to the top. This leads to a rotational motion of the air, which rolls up into a vortex that is a lot like a tornado emanating from each wingtip region. These tornadoes of air, or tip vortices as we call them, have significant kinetic energy. And since that kinetic energy is rotational and oriented in the transverse direction, not aligned with the direction of flight, it does not help the aircraft move forward. Thus, it represents a loss of energy. The thrust from the engines must supply the energy that is lost to the tip vortices. So this energy loss is drag, and we call it induced drag since it's a direct result of lift. The magnitude of the induced drag depends both on how much lift is being produced and how the lift is being produced. A heavier aircraft must produce much more lift than a lighter aircraft in order to stay in the air, and so will have much stronger tip vortices and much more induced drag. Furthermore, for a given aircraft with a given weight, an aircraft moving in slow flight will have stronger tip vortices. This is because of how the lift is being produced. Lower airspeed requires a much higher lift coefficient for sustaining flight. Higher lift coefficients require higher angle of attack, meaning that the wing is essentially working much harder to produce the lift. So the worst case scenario for the highest induced drag is for a heavy aircraft flying at low speed. Surprisingly, this leads to significant drag at low flight speeds, where drag actually goes up as the aircraft flies more slowly. Heavy aircraft, such as a fully loaded Boeing 747 or Airbus A380, will have the strongest tip vortices on slow flight just before takeoff. This is a serious concern for other aircraft flying behind a large heavy aircraft. The strength of these tip vortices is so high that it can cause a trailing aircraft to lose control and crash. One of the big challenges for air traffic control is to provide sufficient separation between these large, heavy aircraft and trailing aircraft that could be susceptible to upset. In fact, air traffic control has special procedures for handling these large aircraft and surrounding aircraft. Let's take a moment to listen to some typical air traffic control communications.
Delta 26 Heavy, wind 180 at 18, gust 28, runway 22 right, clear for takeoff.
22 right, clear for takeoff, Delta 26.
American 7219, Kennedy Tower, caution wake turbulence, runway 22 right, line up and wait.
Line up and wait on 22 right, American 7219.
Okay, you probably noticed the air traffic controller using a heavy designator when referring to the call sign of a large heavy aircraft. And the controller will also explicitly state, caution, wake turbulence. These practices are mainly to alert other aircraft in the area that strong tip vortices are present and must be avoided. In fact, the tip vortex issue is the single biggest factor that constrains throughput at airports. Air traffic control must ensure adequate separation between landing aircraft, so there is a minimum spacing between vehicles. This spacing is based on estimates for how long it takes for the vorticity to dissipate or get blown out of the way by winds. Now, what can the aircraft designer do to minimize the impact of the strength of the tip vortices and the induced drag? There are some tools that the designer has to alleviate these concerns. One of the most significant tools is to change the distribution of lift across the span of the wing. We can think of lift distribution as the fractional contribution of the overall lift that is present at a given span-wise location. The ideal lift distribution is elliptical shaped, with the lift tapering off to zero at the wingtips. This is why the Supermarine Spitfire, a World War II fighter aircraft, was built with an elliptical-shaped wing. With this elliptical lift distribution, the induced drag was minimized. Also, long, slender wings will have much lower induced drag than short, stubby wings for a given wing area. We describe the amount of slenderness of the wing by defining an aspect ratio, which is the square of the wingspan divided by the wing area. For a rectangular wing, this would simply be span divided by chord. High aspect ratio will result in lower induced drag. This is primarily because the distribution of lift across a long, slender wing will result in less of a pressure gradient at the wingtip and weaker tip vortices. A good example of a high aspect ratio wing is the one found on the U-2, a famous spy plane. This is the aircraft flown by Gary Powers during the height of the Cold War to do aerial reconnaissance missions over the Soviet Union before his aircraft was shot down by a surface-to-air missile. One of the key design requirements of the U-2 is long endurance, which is driven by the amount of induced drag that an aircraft has. In order to eke out the best possible aerodynamic performance for this aircraft, the induced drag had to be minimized. So, the U-2 was designed to have a very high aspect ratio wing. The U-2 design is so successful for its mission that it has been operated by the Air Force for over 50 years. Now, the reason that most airplanes don't have much longer wingspans is that they are constrained in some way, sometimes for non-aerodynamic reasons. For example, commercial airliners have to pack in very tightly in the constrained gate environment at airports. With an established spacing between gates, it would be very disruptive for an aircraft manufacturer to introduce a new aircraft design with much longer wingspan. Also, extremely large wingspans pose challenges for the aircraft structural designers. The weight will have to increase to have a structure strong enough to support the large wing, and heavy structure would offset the aerodynamic benefits of that large span. Let's conclude with one last design tool for reducing induced drag, the winglet. These are the vertical fins that are seen on many modern commercial airliners. The selection and tailoring of winglets is actually a nuanced area of aircraft design because the aerodynamic situation is highly three-dimensional and the winglet adds to the overall weight of the aircraft. In general, the impact of the winglet is the same as that of increasing the wingspan or aspect ratio. The winglet alters the distribution of lift across the wing, but without having to increase the wingspan. This ability to increase lift without increasing wingspan, along with the aesthetic appeal, is why winglets and other wingtip devices have become so popular. So we've seen that the effects of lift and drag are interconnected. Aerodynamic stall poses a limit to how much lift can be produced and to how slowly an aircraft can fly. In the stall event, the lift drops off and the drag goes way up. And the distribution of lift across the span has a large impact on the development of induced drag, which is related to the wingtip vortices. Now, our understanding of lift and drag has only come about through decades of study using analytical tools, wind tunnels, and computer simulations, which we'll turn to next.